everybody. My name is Alex Merced, and welcome to this presentation, Open Standards for Open Lakehouses. Okay, so why am I talking about open data standards today? Well, one of the big things about like lakehouses and lakehouse in general is that with a lot of the standards and technologies that I'm going to be talking about today, storage platforms now become data warehouse platforms. Basically creating this whole new use case, this whole new way to sort of like really go out there and get more workloads on those storage platforms. But honestly, after watching a lot of the presentations today, I'm noticing a lot of the techniques that you'll see being used here, trying to prune and make accessing the storage layer more efficient at a higher level, is a lot of the similar techniques that I've seen today at the lower level, talking about like, okay, how many bits do we move and things like that, and where do we move them to and whatnot. So it's always kind of cool to see all the different layers and how they all get optimized in different ways. And today it's definitely been very fascinating watching many of the presentations. But as we begin, let's talk about who I am and where I am from. Okay, so like what brings me here today. Okay, I work for a company by the name of Dremio. Dremio is a lakehouse platform. And what does that mean? Basically what it does, it makes it easier for you to treat your long tail of data, particularly your data lakes, your storage layers, as a full-blown data warehouse. Thus, usually you would call your storage layer like a data lake in the data world. So thus, if you treat your data lake like a data warehouse, data lake house. Okay? And Dremio kind of does this through three main value propositions. One, unified analytics, so allows you to kind of connect all your data sources, so all your different storage layers. So if you have S3, if you have ADLS, if you have MinIO, if you have Fast, Pure Storage, you can connect all of them in one place, be able to query between all of them in one place with our very fast SQL query engine. And if you're using Iceberg, one of the topics I'll be talking a lot about today, one of the things when you start managing database-like tables on your storage, well, you need to do the management yourself. You need to clean up the files you don't need anymore. You need to optimize those files and rewrite those files, and Dremio can kind of automate a lot of that for you, so that way that storage layer can become your primary data warehouse for analytics. And the other really cool thing about us is that we're hybrid. So we can work on-prem and in the cloud. We can be deployed on-prem and we can be deployed in the cloud, which is one of the reasons why we've been partnering up with a lot of storage companies in sort of helping move towards that sort of data lakehouse concept, because we can be deployed on-prem and making us a very sort of key tool to enabling data warehouse-like workloads on-prem with different storage layers. Now, who am I? Well, my name is Alex Merced. I'm a senior tech evangelist for Dremio. I've been with Dremio now 2.5 years, almost 3 years. Man, time flies by. But one of the things that I've been doing more than anything is basically evangelizing, advocating for open standards, particularly when it comes to the data lake. So many of the technologies I'm talking about today, one of the ones I talk about the most is Apache Iceberg, so much so that I ended up writing a book about it. This is literally my 2023 in physical form. It was a long year. Okay, but I will be auctioning off a signed copy of this book. So at the end, if anyone wants one, I have these little cards up here up front. Feel free to fill one out, and then I will announce who gets the book sometime before the conference is over. But basically, again, I spend a lot of time working in the data and web spaces, doing a lot of software development, data engineering. Now I work as an evangelist, and I speak at a lot of events, and I host a lot of podcasts. So if you enjoy a lot of the stuff I have to talk about today, there's lots of other content online on YouTube and on Spotify and iTunes of me talking about these things, because I talk a lot. Okay, but as I mentioned, not only can you get a physical copy of the book, but you can also get a free digital copy of the book. So if anyone's interested in getting a digital copy of the book, you can scan this QR code right now, and you'll have a digital PDF of the whole book and get all the detail on Apache Iceberg right in a PDF form. Okay, I'll give everyone a second to scan that. Okay, and for those interested in learning even more about Apache Iceberg, I am currently doing a 10-session course. We're getting towards the end. I think we're on session 8 now, but all the sessions are on demand for those who want to watch those courses afterwards. All the stuff can be found, and again, if you don't scan it today and you want to get access to it, just message me on LinkedIn. And if you haven't added me on LinkedIn yet, please do. I do try to keep everyone informed on this area. And again, I mentioned I host a lot of podcasts. Okay, there's a link to download slides. I'll share that again at the end. But what are we going to be covering today? What we need to talk about today is, first off, what is a data lakehouse? I've kind of already summarized what a data lakehouse is, essentially using your data lake as a data warehouse, data lakehouse. But I'm going to go a little bit more in detail about that. Then we're going to talk about the sort of standards that actually have made this possible. Because it isn't necessarily a new idea. People have tried to use their data lake this past as a center of analytics. It just wasn't there yet. And these pieces kind of help make it possible. So Apache Parquet, Apache Iceberg, Apache Arrow, and Nessie. So these will be 4 open source technologies I'll be talking about, providing sort of open standards on which to kind of build these kind of modular platforms. So let's start off with, what is a data lakehouse? So to appreciate what a data lakehouse is, we need to understand data systems that came before data lakehouses, and even before data lakes. Okay, traditionally what happened is we'd store data either in databases or data warehouses. Okay, and the great thing about databases and data warehouses, like Postgres or MySQL on the database side, like Snowflake or Redshift on the data warehouse side, is that they would abstract a whole lot of stuff from us, so we don't have to deal with it. I wouldn't have to deal with how the data is stored. Okay, I don't think about it, it's just there. Okay, I don't have to deal with how does it know which data is part of which table. Okay, how does it know table A from table B? Oh, it just works. How does it know that there's table A and table B? How does it keep a track of all those tables? A catalog, okay? And when I write an SQL query or a SQL query, depending on how you like to say it, how does it know how to parse that SQL statement? How does it know to turn that into like relational algebra, create a query plan, and then execute that plan? I don't have to worry about it. I just write my SQL, Postgres runs it, Snowflake runs it, it's all good. Now this is all fine and good. The problem becomes, as you get to higher and higher scales, particularly for analytics, is that each system is basically vertically integrated. So it does it differently than the other one. So if I want to use multiple systems, I'm making multiple copies of the data between each system. Okay, and that gets really expensive really quick. I'm paying for double the storage. I'm paying for the time it takes to move the data. I'm paying, when you're working in the cloud, you might be paying egress fees. You know, it adds up. So especially when you get to start getting to like petabyte and beyond, I'm starting to think, like, is there a better way to do this? And again, oftentimes databases, we're thinking about row-based data structures, and data warehouses, we're thinking about columnar-based data structures as far as like optimal ways of storing the data. But only if there was a place where I could just dump the data and it just becomes the one place I need the data. I don't have to make any more copies. I don't have to move it around anymore. There is a place like that. It's called the data lake. Essentially, right now, as traditionally what you would do, and I mean traditionally, I mean is like in the last 5, 10 years, you know, because things move so quickly. So basically what you would do is that all your systems would just leave a copy of your data in your data lake, in your storage layer. Again, on the cloud, you think like S3 or ADLS. On-prem, it might be like Hadoop, MinIO, VAS, Pure Storage. Again, there's a variety of options. But you would land it in your storage, and then you would use tools that can access that storage to run ad hoc analytics, whether it's on a CSV file, a JSON file, a Parquet file. Those tools would be tools like Dremio. That's one of the things that we specialize in. Or AWS Athena in the AWS ecosystem. Lots of variety of different tools in this space. But the thing is, when Dremio runs a query in your data lake, it might see like 100 CSV files, but it doesn't necessarily know that they're like one data set. Okay, it doesn't really think about it inherently that way, and doesn't have the kind of statistics that a database would have to scan that efficiently. So it's scanning every file to accomplish a query, which is not necessarily scalable. So what we need is to kind of reintroduce those layers that are missing. And that's how we get to a data lakehouse. We take the storage that we already have, somewhere to store the data. We have tools to query the data where it's stored. But what we need now is a table format that's going to allow us to treat those 1,000 files as one unit. Give us the statistics to scan that unit efficiently. And a catalog, so that way I can identify how many of these tables that I actually have sitting in my storage. Okay? And once we actually introduce these pieces, well, now basically there's nothing you can't do on your data lake that you couldn't do in a data warehouse like Snowflake or Redshift or Synapse or whatnot. You can now pretty much just operate directly off your data lake. Okay? Now again, it's a space that's continually advancing and improving, but essentially that's the idea. The idea is like, okay, I can just have all my data in one place. All my tools can talk to it. So in that case, now I'm just focusing on what workloads I need to do instead of having to think about how am I going to move the data from place to place and keep it consistent. So what things made this possible? Well, as I mentioned, like CSV files are great. We love CSV files. You know, we oftentimes will take our Excel spreadsheets and turn them into CSV files, or you know, everything spits out a CSV file. Problem is with CSV files, JSON files is they're text-based. Okay, so that means they're going to take up a lot more space in storage than not text-based. Okay, and so that's one problem. Two, they're generally row-based, particularly CSV files. They're row-based structures, and that's not optimal for analytics. So, yeah. So what happened is that they came out with a file format called Parquet. This is a binary format, okay, that's columnar. So basically the data is now stored in columns, which is better for analytics. And two, since it's binary, it's going to take up a lot more space and can be compressed because of the way it's structured. So you can get really, really high compression, taking up a lot less storage, but also being able to access the data much, much faster. Okay? So essentially, again, we're going from a row-based layout where we lay out the data like row 1, row 2, into a columnar layout where basically we have all of column 1, then all of column 2, all the records for column 3. But what's really cool about Parquet, like right there, you've already gotten an improvement. Okay? Just by going binary, the compression, the columnar format, you're already getting performance benefits. But going beyond that, what Parquet does is that in those files, it actually breaks up those columns into chunks of rows, row groups. Okay? So now I may have a gigabyte Parquet file, which we'll just say represents 1,000,000 rows. And it might be chopped up into 4 groups of rows. So each one would represent 250,000 records. Okay? And then each of those row groups will have metadata or statistics that I can then use to decide whether I even need to scan or read that row group. So now if I'm Dremio, a query engine, and I'm opening up this Parquet file, because of its just nature design, I can load up the file really quick. But then as I go to each row group, I can take a look at the statistics and determine if I can just skip that row group altogether and not bother reading it in full. Okay? Which speeds up the process. But again, this is just one file. Okay? This is where the next step is going to come in. But essentially, that's what Apache Parquet does. It gives us this really nice, much more smaller file that's going to be much faster to read, much more faster to prune with all the statistics inside of it to scan for analytics. But again, one Parquet file, well, I mean, eventually you hit like a gig, and you might say, okay, I'd rather have like 1 gig per Parquet file, let's say. Okay, again, depends on your memory and the particular cluster you're using to run analytics on this thing, but we'll say a gig. So what if like my data set's like 100 gigs? Well, then that'd be 100 Parquet files. How would Dremio know that these 100 Parquet files are one data set? Inherently, it wouldn't know. I mean, Dremio has ways of handling that, but there's not a standard way of doing it until nowadays. Nowadays, you have what these are called open table formats. And these open table formats solve that problem. They'll say, okay, hey, you have a bunch of Parquet files that make up one data set. How do we know that it's one data set? What we'll do is we'll write metadata in separate files and identify. And there's right now 3 main formats for this. Apache Iceberg is the one I'm going to talk about today, but there's also Apache Hoodie, and there is Delta Lake, which are sort of the 3 main formats. And then there's a 4th one that's kind of coming out right now called Apache Pymon that came out of the Apache Flink project. So what does this do? It basically, this is like the missing key. This is really when we go from data lake to data lakehouse. Because basically the thing that we're really missing from databases is asset guarantees. The ability to know that when I do a transaction, that transaction is going to happen or it doesn't. To know that, hey, if me and Bob access table A, that we're looking at the same data. Consistency. That if I'm reading to the table and someone else is writing to the table, that we're not going to affect each other. Isolation. And the fact that I know the table will be there later. Durability. I mean, we already had durability. We were storing the data on the storage system, but those other 3 we kind of lacked. Okay? And this kind of fills in the gaps. So what Iceberg is, okay, is essentially a metadata standard. It's a standard of ways to write different stats around that group of files that allows a tool like Dremio to be able to consistently always read the table the same way. So basically 2 different tools, like if Dremio is running a query, AWS Athena is running a query in the same data set, they're going to see the same data because they're accessing the same metadata. It also makes sure that both, let's say I'm doing a write on Athena and I'm doing a write on Dremio, and they're happening at the same time, they're not going to collide because of the mechanics of the metadata. Okay? So basically, it basically provides those asset guarantees. But on top of it, it provides statistics that we want to scan this group of files. I can say, hey, you know what? There's 1,000 files in this table, but based on the statistics, I really only need 30. Okay? Imagine that. Instead of scanning 1,000 files, I only scan 30. And then again, those are Parquet files. So once I scan those 30 Parquet files, I can reduce that further through those row groups. I'm really starting to speed things up. And again, this is all just at the pure software layer. So now, again, I'm scanning tables that are sitting directly in my storage, not in a database system or a data warehouse system, and I'm getting the sort of same dynamics, the same performance as if it were in a data warehouse or database system. Because this is that missing piece, the statistics that a database would typically have internally. Okay? So again, Apache's Iceberg approach is to kind of put it in metadata. And you have 3 layers of metadata. And this is all files that get stored on storage. Okay, so everything is done. So unlike a database or a data warehouse where you have this continuously running system, and that's tracking everything, with Iceberg, they're just files. So basically nothing is running in the intermediate. So you can also spin down and reduce your compute costs because you're not running some system to track these tables 24/7, which is another sort of incidental benefit to this data lakehouse approach. You just run compute when you need it. Okay? Now, you have the metadata files. So this is like the top level of the metadata. So this basically tracks like, hey, this is a table. This is the schema of the table. This is how the table is partitioned. All these things. And also, these are the historical snapshots of the table. And it's from there, Dremio can then identify, oh, okay, well, basically this metadata file tells me that there's 2 versions of the table, 2 snapshots. Well, the user didn't specify, so I'm going to assume we want to look at the newest snapshot. So in that case, that's going to point me to this manifest list, which essentially each manifest list represents 1 snapshot, 1 version of the table. And what that does, the manifest list, which again, here's where the terminology gets a little funky. The manifest list is a list of manifests. That's a tongue twister, okay? So essentially, what does that mean? There's a bunch of these individual manifest files. Each manifest file is a group of files. So say, hey, these 20 Parquet files, these 20 Parquet files. And the reason why they're broken up into multiple files is for reusability. So that way you can reuse them as different versions of the table happen. But also, they generally split them up by partition. So let's say I have a table of voter data. And I'm partitioning the data based on like political party. So basically, there'll be a different manifest for red voters, for green voters, for yellow voters, for blue voters, each one tracking it. And then it's the manifest list that says, hey, these are the groups of files that make up this version of the table. Okay? But this has statistics on those chunks. So now Dremio can say, hey, let me take a look at each chunk of files, take a look at those statistics, and see if I even need to scan that. So instead of getting rid of each file one by one, I can actually just drop big groups of files and just say, hey, I don't even need to scan these. And then I can go to these individual manifest, which lists the individual files, take a look at those stats and say, this file I don't need, this file I don't need, this file I don't need. So instead of loading up every file into memory and having to retrieve it from storage to do so, I can just read these metadata files, prepare a list of files that I do need to scan, and then go scan them. Okay, basically really reducing the amount of work that has to be done to accomplish the same query versus before. Okay, and that's essentially like the role of these open table formats. Okay, they basically provide that metadata to just be able to go about scanning your storage much in a more smarter way for analytics for that specific use case. So again, Iceberg is going to basically provide this level of abstraction over those physical data files that enables things like concurrent writes. There's a feature called hidden partitioning. Just to summarize this, because I can talk about this for like 20 minutes. Just to summarize that, it just basically makes partitioning, how you chunk out that table, much easier to implement and much easier for the data analyst to consume. So Iceberg doesn't just care about giving you that abstraction, but also cares about the ergonomics of that abstraction, which is very important because people are going to adopt things that are easier to use, okay, that make their lives easier. Okay, you have schema evolution. That's something you could do in databases that you couldn't really do in the data lake before. Okay, you can optimize the data. Basically, Dremio and other vendors offer auto optimization first services. Now they have CDC built into it. You can do efficient updates. So basically what happens here is that there's different paradigms for how you actually write to the table that can be used for different use cases. Won't get too into the weeds there. But bottom line is that it basically gives you the benefits of a data warehouse directly from your data lake. But here's the thing. Let me go to the next slide. I think next I'm going to do with Apache Arrow. Now I've identified which files I want to read. So basically with Iceberg, I have 1,000 Parquet files that are part of a table. I determined that I only need to read 30 of them. Now since they're in Apache Parquet files, I don't have to read the full files. I only have to read up half the file, a quarter of the file, depending on the stats in those row groups. Now I've read all those files, but I need to actually do the processing. Okay, I need to actually execute the query now. So now when I load the data from those Parquet files, how does that get represented in memory while I'm processing the query? That's where Apache Arrow comes in. Apache Arrow was actually partially born out of Dremio. It was actually Dremio's in-memory format before it became the open source project Apache Arrow, which is now all over every data tool. Okay, But essentially what it is, it's a columnar format again, because columnar is better for analytics. But it does it in a way that, one, allows you to store the same data in memory in a very condensed way, but it's also organized in a way that allows you to process data very fast in memory. So basically now everyone is adopting Apache Arrow to make their processing faster, because just by switching out the structure of how you represent the data in memory, you're getting a lot of performance benefits. So again, I'm reducing the number of files I have to scan with Apache Iceberg. I'm reducing how much of those files I need to scan using Apache Parquet. And then when I load those files, I'm loading them up into a really fast in-memory format. And this is how now you're starting to see how all these things, when you put them together, you start getting that data warehouse-like performance. Instead of having to have a very coupled system with a really high price tag, I can now take my existing storage layer that I'm already paying for and turn that into my data warehouse. Now, so Apache Arrow is an in-memory format. It's not just that, though. Basically, the project, what it does is that it creates libraries in every language. So there's like a Rust library, a Go library, C++ library, JavaScript libraries, Ruby libraries, all the languages, or most of them. Libraries for you to work with the format. So basically, in any language, whatever your tool is written in, you can adopt Apache Arrow if you're creating like a data processing tool. Okay? So basically, and what it does is that, again, it just gives you all the tools for one to turn data sets into Apache Arrow, to run operations on Apache Arrow. And again, right now it supports 12 different languages. It was co-created out of Dremio and from Wes McKinney. Wes McKinney is probably most famous as the creator of Pandas, which is a really popular data processing library in Python. It was really adopted really quickly, like the chart right here. So you can see how the downloads escalated really quickly for using this library in data tools. And you can see lots of data tools are embracing it. And companies are embracing it, and it's just everywhere now. But the thing is, just because I load up the data really fast in memory, there's still another bottleneck. Because the data just doesn't exist on that machine. That data has to be sent over to another machine. Okay, especially if you're talking about large clusters of machines doing the data processing, they got to send the data between each other, and then they eventually got to send the data to the client. And the old standard was JDBC, ODBC. Still generally a standard for accessing databases. The problem with JDBC, ODBC is that it's row-based, which is great for transactional data. So again, if this was my point of sale system, that would be fantastic. But for analytics, where the data is generally structured as columnar, not ideal. Okay, because what would happen is that I'd have all this data that's set up in a columnar way. I'd have to convert it into rows, that send it over by JDBC, and then reconvert it again into columnar on the other end. Okay, which just adds a whole lot of processing time to the whole deal. Okay? So basically, Apache Arrow Flight is a solution to that. Basically, a standard, a network protocol for sending that data via gRPC over as a columnar format. So basically, you don't have to serialize and deserialize because you process it as Arrow, you sent it over as Arrow, and the system at the end knows how to use Arrow. So in that case, you just save yourself all that time. And when you have lots and lots of rows of data, that really adds up. I do have a video on YouTube where I did like ODBC versus Arrow, and I did like increasing numbers of rows, and you can see like it took a while for ODBC to finish the job, while like Arrow Flight was done like in a few seconds. So it really does make a difference. Okay, but again, it's designed for, and then not only is it like, again, columnar, allows you to move Arrow data, but the really cool thing about it is that it's just general design of the API itself enables parallel processing. So generally the way the structure is, like you would make the request, but instead of just getting an immediate response with the payload from that request, it actually gives you like a ticket, and then you can actually go to like different nodes and say, okay, hey, I got this ticket, and get portions of the data from different nodes, so that way you can deliver that data quicker across like a cluster. So it has like parallelization designed into it. Ooh, tongue twisters. Okay? So it enables parallel data transfers. Okay? And again, here's an example of like just like the performance differences. So again, here we have 2,000 records. Between ODBC and Flight, not much of a difference. Like at that point, either one's fine. But when you go to 5 million records, huge difference. And then we go to like 1 billion records, even bigger difference in how long it takes with ODBC, because again, everything's got to first get converted into rows and then converted back into columnar once it hits the other end. So you're paying the cost for all that conversion of the data. Okay, and then Aeroflight SQL, just kind of getting the punch, so that way make sure I get through the whole presentation and give you guys time for questions. But basically what this does, it just makes it easier to send SQL over the Aeroflite protocol. So basically, they just created some endpoints and added some functionality to the API to enable sending SQL directly over and getting a response to that SQL. Okay? Cool. Okay, and then there's some other innovations in this space. So basically now there's actually a ODBC JDBC driver. So that way you don't even have to change the way you do things. You can just swap out your ODBC JDBC driver, and if the tool, like a tool like Dremio that supports Aeroflite, is what you're connecting to, you can use this driver and connect to it and get all those benefits. So you have that. And then there's a new ADBC protocol. So this is the next, and this is the final innovation I want to talk about, is that that's great to be able to use JDBC, ODBC with Aeroflite, but not every columnar tool, like other databases and data warehouses, or other data warehouses really, they also store data as columnar format. And they would also like to send data over the wire in columnar format, but they're not using Apache Aero. So they can't really use Apache Aeroflite. So what they did is they created a protocol like JDBC called ADBC, where you can actually have drivers for other columnar formats. And you can go connect to like X data warehouse using their format, and you just plug in their driver in the same way you would use JDBC ODBC, but it transfers the data over in a columnar format. And that's the newest piece of the project. So yeah, cool. Okay, so just to summarize, again, I got Apache Iceberg that identifies my table, gives me data so I can say, hey, 1,000 files, I only need to scan 30. Then I got Apache Parquet, who's those 30 files that have stats that can say, hey, I only need to scan half the file. Okay, and then once I scan that data, I scan it as Apache Aero, okay, for really fast processing, and I can send it over to another machine really quickly because of Apache Aeroflite. But the thing is that at the very top of that, I need to know those tables exist. And generally, when it comes to Iceberg, the way you know those tables exist is through a catalog. Okay, so this will just basically be, think of it as like a process that's running like a phone book and saying, okay, hey, table A, metadata is located at this storage location. For table B, the metadata is at this storage location. But Nessie does that, but it's so much more. Okay, it actually adds this whole new level of catalog versioning. So Git, I mean, Git's probably part of all of our daily lives, right? I love Git. Okay, I can spend all day just playing around with Git. And why do we like Git? Because I can make a branch. I can isolate changes to my code. Okay, I can tag commits, so I can easily go back to those commits, things like that. Now, I can do that with my tables. Okay, with Nessie as your catalog, I can do all that Git, branching, tagging, Git-like stuff, but do it at the table level on my catalog. Okay, so when we think about the evolution so far, we start off by having columnar file formats, Apache Parquet, as we talked about earlier. We then moved on to like open table formats that gave us those asset guarantees, so that way we can do those kind of operations right there in those tables. Okay, and now the last evolution is this whole data as code paradigm, which is what Nessie enables, that allows us to bring those Git-like semantics to that data that's sitting in our storage layer. So again, we're really bringing the full gambit of like data warehouse-like features directly to your storage layer, okay, outside of a data warehouse system. Actually, this goes even beyond what data warehouses offer now. So again, when you take a look at a data lakehouse, what are the pieces that make up that data lakehouse? As we mentioned, a columnar file format, Apache Parquet, a table format like Iceberg, a catalog like Nessie, okay, and then basically all those tools, so again, Dremio is one tool, Spark, Flink, these are all different tools that can talk to your data. They would connect to your catalog and say, hey, I'm looking for table A. And then would point to where the metadata is, and then using the metadata, I can recognize which files I need to scan. And you've basically, what you have is a deconstructed data warehouse. That's essentially what it is. All you're doing is taking what a data warehouse would do, deconstructing it, so you can modularly piece it together. It's very artisanal. Just kidding. These are the jokes. Now, continuing on with like evolution, so essentially what you have now, okay, is when you take a look at your storage layer, before you had a bunch of files, but now your files are organized because of the metadata. It recognizes saying, hey, this is the version 1 of the table, which points to these data files. Here's the newest snapshot of the table that points to these data files, okay? And then Nessie keeps track of those references. So for example, what you see here, and I have another visual of this coming up, what you see here at this point in time, table 1 is pointing to the V1 of the table, table 2 is pointing to V2 of the table, okay? And then we branch. I have another visualization of this a little bit that I think is a little clearer coming up. Okay, but then all your tools can then access this. Cool, okay, here's the visual I was just talking about. So essentially what would happen is that a query comes in from a tool. just say Dremio, Athena, whatnot. It hits the catalog, and it goes to the catalog and says, hey, Nessie, I'm looking for table A. Well, what happens is that the catalog has a listing of each table, and right now I'm listing like the version of the table, but really what it is, it's a storage location. It'll be like S3/ where that newest metadata file is. That's really what's there. But essentially, it's a listing of that. So, but what happens is that every time that listing changes, Nessie makes a full commit. Usually other catalogs, they just change it and then you just move on. There's no historical versions of those changes. But in Nessie, keeps track of that. So again, each one's a commit. So right now, table A, table B, table C are all version 1. Okay, I make a change to table B. So now the new commit, the new version, when I take a look at the head of my history here, table B is now pointing to version 2. Okay, but let's say I want to make some changes to the table. Well, I can make a branch. And so basically all my queries for my production users, they're going to hit the main branch. So they're going to be querying this. Their queries are going to hit this. But maybe I'm the data engineer and I want to isolate some ingestion work. Well, now I can create a branch and those changes are invisible to my production users. They don't see all these commits that are happening until I'm done and I've validated the work and I merge it back in. Okay, and then basically, ta-da, now all that data has been simultaneously published. So you're talking about like multi-table transactions. Another really cool use cases is zero copy environments. Like one example that a lot of our financial customers and financial industries use is that they have to do stress testing, right? Like every day, because of different regulations, they have to kind of take a look at all their financial numbers, do tests on what does it look like in the worst case scenario, and then do that again every day. Okay, that requires them to make a copy of their data, manipulate that data for all these scenarios, and then get rid of that copy of the data. But with Nessie, I can just create a branch that's not a copy. Okay, in the same way Git's not a copy, or just basically it's just a different history of how you add and change lines of code. Same thing here, it's just a different history of how the snapshots changed. So in that case, you can create a copy of the environment without creating a copy of the data, do all those changes, run all those tests, and at the end of the day, just dump that branch. Okay, and now you've spent a fraction of the cost to be running those tests every day, which is really cool. And you can also tag commits. So that way, if you want to do like for AI, where you need to maybe test the data against a very historical benchmark, well, you can make those benchmarks easy to mark. Okay, so again, you get catalog level versioning. So it's across multi-tables. Okay, not just a single table. It's open source. Everything I've talked about today is open source. There is a managed service. Dremio has a managed Nessie service. That's part of our product. It's cloud agnostic. You can use it with any cloud. Actually, you can use it cloud or on-prem. It's not dependent. It's hybrid. And again, storage agnostic. You can use it with any storage tool. So it's just this universal catalog for tracking your tables that give you these benefits. Okay, and again, there's tools for optimization. Okay, this is just going to reiterate what I've already said. So again, this allows us to isolate and version control our data. That's the beauty of it. Also has some governance features. It enables data warehouse-like transactions. So again, let's take a look at what the paradigm was on a data warehouse. So on a data warehouse, usually what you would do is to do a multi-table transaction, you would write some SQL that looks like this. You would begin a transaction, then you would write several different SQL statements, which would then end in that transaction. Okay? And you would commit the transaction. Now in Nessie, you just create a branch, and then you can actually not only do multiple transactions, they don't all have to happen right now. They can happen across multiple tools. They can happen by multiple users. Okay? And you just merge the branch whenever you're ready to merge the branch. Okay? So I can have like some data come in from Kafka, some data come in from a database system, some other ingestion from Spark, some transaction from Dremio. All of this stuff is isolated, unseen to my production until I eventually inevitably merge the data and done. Okay, that data gets published. Okay, very, very simple. I mean, especially for someone who, if you use Git a lot, like that just seems like a very intuitive way of doing things. Okay, and again, it works with all engines. So every tool can kind of work with Nessie. Cool. Okay, so now we're at the end of the presentation. So now we're going to get into the credits. Okay, so one, if you want to get hands-on with this and actually try this out, I have several tutorials that make this really easy. Basically, it's all no have to spin up any infrastructure, no cloud, you just Docker. Okay, all you need is Docker, and these tutorials will walk you through setting everything up on Docker and actually getting hands-on with all the technologies that I've talked about today. So you're literally within literally 5 minutes, you'll have like Dremio, Minio, Nessie running on your laptop. And again, feel free to swap out the storage layer however you want. But you can run these exercises, actually see this firsthand. So everything I'm talking about, actually by making your storage layer work like a data warehouse, you can see it firsthand and see the power of what I'm talking about and what it can do for others who are in the analytics space. Okay, so again, the idea here, this really transforms a whole new space of what you can do with your storage. Okay. Also, this week, I have another event that I'll be doing here while I'm here in Santa Clara. On Wednesday night, I'll be doing this event over there actually at our Dremio offices. So if you want to actually see Dremio HQ, you can come on down. There'll be free food. You can come hang out, where we have 3 talks all about Apache Iceberg. So it's just going to literally be a whole night talking about Apache Iceberg, another tool called Apache Polaris. So we have me from Dremio. We have Yufei from Snowflake, who's actually one of the main committers for Apache Iceberg. Waymo Liu, who's the founder of PuppyGraph, which is a really cool startup doing graph queries on Apache Iceberg. So and think about that. Now I only have one copy of the data that I can do graph and relational queries against. Okay, I don't have to be moving into different systems for different types of data or different types of paradigms. That's really cool. And actually, I'll leave that up there for a moment. And before I open questions, I always like to make sure I feed the social media gods for work. Okay, so does everyone mind smiling for a moment while I take a quick photo with all of you? If I can do this right. There we go. Awesome. Okay, thank you very much. And then again, at the end, if you guys want to follow one of these cards, you can be in the raffle to win the physical copy of the book. We have some free Narwhal plushies if anyone wants one. They're pretty nice and they're fun to squeeze. But with that, I'll open it up to any questions anyone has on anything I talked about today. Go for it. Mm-hmm.
I think of that as being row-based data rather than columnar-based data. But in your table, you showed it as already being columnar-based data. So what's the best practice?
I mean, I guess it depends.
The transformation, from row to columnar?
Wrap it up. Okay. Repeat the question. Okay, got it. So the question is basically, when do you distinguish it between versus like when it should be row-based, when it should be columnar-based in the data lake? Mm-hmm.
Transformation until you're actually doing the query to use the data.
Mm-hmm.
So if you've got things dumping logs in there in row-based formats, it's always the latest data.
Okay.
Transformation steps in columnar-based data before the analytics.
Yeah, I mean, it depends. It depends where the data's coming. Sorry. Yeah. Okay. So bottom line is, okay, when should the transformation occur, or like what's the best practice for that? Okay, because typically what happens is that most systems would probably dump the data out in like CSV or JSON format, so you generally already have it. Now, there's a couple different ways that you can handle that. Like some systems, they're just going to be dumped out in CSV, and there's going to be some other step later on to transfer that into something like Iceberg. But nowadays, like things like Flink, things like Apache Kafka, Upsolver all have tools for like taking streams and just landing them as Apache Iceberg. So that way, it just initializes as Apache Iceberg in your data lake if it's going to be used for analytics. So that becomes much more doable. The way to do that is becoming better and better. Even Dremio, we have a new feature called auto ingest, where so basically as those CSV and JSON files land, we'll immediately trigger that and turn that into Iceberg. Of course, you're going to get the most real, like if you want like the most real-time latency, chances are you're probably going to want to use something like Flink and do like live queries going into sync and build a dashboard like as the data is being streamed through. But if you're talking about like BI dashboard, things like that, and you want to build those BI dashboards directly off your data lake, then the data lakehouse pattern is going to make a lot of sense. Or even if for data you want to have served up for AI or ML later on, having that data kind of already in an optimized format from the get-go. So it depends on the particular tools that the data is coming from, because some tools, if you can feed it into a Kafka stream, then I can use Kafka Connect to just land an Iceberg right away. Also depend, but if not, if it just outputs CSV files, then it lands in CSV, I can use something like auto ingest to just automatically convert it, but you still do have that initial step. There's that latency there then. But yeah, again, it depends on the workload. But yes, traditionally data lakes, what happens is that most of your systems do output everything as CSV and JSON, so you typically would have row-based system data initially. And that was one of the main use cases for Dremio, where you can kind of model that data. So you could actually have all your CSV files on your data lake, you would model it in Dremio, and then you have a feature called reflections that would build out the Apache Iceberg table under the hood, so you wouldn't even have to be aware of it. It would just exist so that when Dremio queries it, it's faster, without the user having to worry about multiple copies of their data. But there are, again, depending on the scale of the data, depends on whether you're better off using reflections or you're better off being natively in Iceberg. The larger the scale, to say, the more it becomes appealing to be natively in Iceberg. Yep, other questions?
So you compare the SQL transactions and the data code branching and merging. What happens if you have a data conflict?
Okay. Well, okay. So basically, the question here is, if you're making changes and you're capturing those commits in Nessie, what happens if you have a merge conflict like you would in Git, right? Like in Git, if I have if I merge in 2 different branches and they have commits at like different time points, changing the same line of code, I might create a commit. So this could be a possibility with Nessie, where you might have 2 branches made, making changes to the same table, and you want to merge them, and there's a commit. Now, best practice, I would say, is generally I would try to keep it to where there's only 1 branch making a change to a particular table at any particular time. They are part of the future of that project is to capture more metadata, like for the catalog to collect more metadata around the files to be able to reconcile those changes better. What you do have now is that you do have ways to override and say, okay, hey, I want to force the commit, or only force the commit for these tables, but not for these tables. So you do have some granularity to kind of make those transactions merge. And we just built that into the Dremio SQL dialect, so that way you can take advantage of those benefits without having to like make curl calls to the Nessie server. But that would be the answer there. So like there's ways to handle it, but it's not as granular as it will be in the future. Was there another question in the back? No. Oh, going once, going twice. What?
Yeah, one question. So with Nessie's Git-like semantics,
Mm-hmm.
the way to think about it is whenever branches create, it's kind of like an incremental snapshot so that you don't have a full copy of the data.
That's exactly right. So basically what happened here is that he's saying, okay, when you think about Nessie and you think about the way it handles Git versioning, what it's doing is that each commit is really like an incremental snapshot. So in the same way that like every Git commit is like an incremental change in the lines of code, here it's an incremental changing to that listing of tables with the references to where those files exist in storage that you can then traverse and time travel and all that, just like you can with Git. So that was a perfect way of saying it. Yeah, it's just like incrementally. Perfect. And yeah, any more questions? Nope. Okay, then I'll put up the last slide. For those interested in data lakehouses, I do have a whole data lakehouse Slack community that I run. I travel a lot and speak at a lot of different events, so I do have groups for all the different locations that I travel to a lot. So there's even a meetup Santa Clara. Feel free to post your own events in there, and network, and just another place to hang out. And you can message me there if you ever have questions, or LinkedIn, whatever. But yeah, otherwise, thank you guys all for coming and hanging out with me and letting me talk about my passion, Data Lakehouse, for the last hour. It's very appreciated, and I hope you guys found this interesting. And I'll be around if you guys want to talk more. Thank you.